My name is Mark Benton. I'm the engineering manager and the active products manager for TE's Rugged Fiber Optics business unit. And I work with Mike and Jason in the Aerospace, Defense, and Marine business unit. And today we're going to talk not just about embedded systems, but we're going to talk a little bit just about where you find optics in the different levels of what you'd think of traditionally as electronic packaging. And our business unit's function really is to look at that from the very first transfer of copper data, converting it to optical to the other end of that link and trying to find a way to find solutions for our customers. So why use fiber in a harsh environment? I think you've heard a lot of the advantages already today in the other speakers. Data, bandwidth, distance. I mean, typically you think of 1,000 times the bandwidth and 100 times the distance, hundreds of times the distance very easily. But there's a lot of other places where fiber plays because of size and weight. You may be running signals through a harsh environment, and the last thing you want is a copper conductor and data and signals through there. Security, it's hard to tap. I mean, a lot of these points have been touched on by other folks already today. When you think about traditional electronic packaging, it really starts at level one, which is that packaging of the very first device. And then you move through level two, where you get that device onto a board, and then you connect boards together, and then you connect subsystems together. And by the time you get to level five, you're talking about IOs from subsystems to boxes. And then finally, the connection at level six from a box to another box that may be close, maybe kilometers away. It depends on the application. So walking through the first level, here you're really looking at the optical equivalent of a chip on a wireframe or a chip on a chip carrier. It's that first level of connection to the outside world. The optical equivalent is some form of coupling a laser or a detector to a waveguide. You may use optics, you may use cleaved fibers, you may butt couple fibers to devices. You may be doing discretes, as you can see in the lower right, or you may be doing arrays, which is the picture next to it. All of those things become basic elements that take you to the next level. In the optics world, that may be the traditional solder the lead frame to the board, or a socketed device, or a CPU, or a memory socket. In the optics world, now you're into pluggable transceivers, or the subassemblies inside those transceivers. They can be discrete, single channel 10 gig devices, or they can be the array devices that power the parallel transceivers that several of the folks here have already spoken to. But the trend that you see there is two things have continued to happen. The speed's going up, and the density of the optical connection at the transceivers is rapidly moving away from discrete single channel devices to array-based devices. When you move to the next level, there have been a lot of advancements in the copper world. I don't argue with Mike about that. Clearly, you've seen the evolution from VME up through 25 gig capable RT3 connectors with 56 gig on the horizon. You can see similar trends in stacking connectors, where you started at PMC rather, and today you're up to FMC and FMC plus, and others spoke today about how some of the technologies coming to bear there to increase the speeds through those connections. If you look at the systems that have those embedded transceivers on them, you can see how that's kept pace with the evolution to parallel transceivers. Or if you look at VITA 66.1 and 66.4 as an example, there you've moved from 2 12 fiber or 1 12 fiber ferrules to solutions now in 66.6, where you have up to 224 fiber ferrules in half the space. So you've increased the density at the card edge, and that's been driven dramatically and directly by the amount of transceiver capability that's on the card behind those interfaces. And likewise, as the processing power of the cards has increased, you see a trend of moving some of those transceiver functions off the middle of the card and toward the card edge to free up more space for computing power on the cards. The levels blur when you look at some of the technologies that you apply to solve different problems. You could argue in the VPX world that a level 4 solution is a level 3 solution. You have a processor, you have effectively a subsystem on a card because of the computing power. But you can see how over time on the copper side, the RF density's increased, the bandwidth's increased. If you look at multi-gig and nano RF, both as in size and density trends. And on the optical side, what you see is as densities increased, systems are increasingly moving away from discrete contacts, be they physical contact or expanded beam contacts, and they're moving more and more toward MT or array-based solutions just because of the density of the optical I/O that has to be supported. And when you look at those contact termini technologies translated into the connectors that are used, the trend you see is a move away from bulkier, discrete solutions to more array-based, smaller, more densely packaged circular and rectangular connectors. And you also see a trend where that array technology is now moving into the world of optical flex, as some of the other speakers talked of today, where you can actually use the flex circuit to do some of the rerouting within your interconnect and eliminate an extra layer of circuitry or an extra layer of optical conversion, depending on how you're approaching it. So you see that trend both in level 3 and in level 4. For example, you can build an optical flex circuit today in such a way where the connections behind, say, your Vita backplane interface on the daughter card can be done in such a way that when you assemble the system, you can only put it together one way and you get it correct. There's no way to miswire, there's no way to mishandle it because you've built the system to allow you to do that properly. If you move to level 5, what you see is the trends in copper have taken advantage of the speed and modularity of some of the standards like AirInc and others. And there are now copper solutions both on the cabling side and on the contact side that let you increase speed and do things like run gigabit Ethernet over these connections from the boards to the backplanes. And you can use high-speed laminates and copper rigid flex combinations to route electrical signals high speed to the cards, from the cards rather to the back to the I/O panel. When you look at where optics has trended, you see things that started as discrete solutions where you'd have a discrete couple of optical contacts and an otherwise electrical connector. That's now transitioning to those discrete contacts becoming array-based connectors because of the evolution of the transceivers. And likewise, when you look at the harnessing that you might use, again, you see a trend away from discrete connections to MT-based, ribbon-based solutions. And behind those ribbon-based solutions, again, you can have ribbon fiber, but you can also have a fairly complex optical flex circuit. And level 6 is where you get into some of the interesting solutions where you're trying to actually move from box to box. Sometimes that can be a very short distance. Sometimes that can be kilometers or tens of kilometers, depending on the system that you're working with. When you look at the copper side, there have been a lot of advances in the cable and in the ability to develop connector systems to take advantage of differential signaling and isolation and noise cancellation features, to the point where you have things like the C-Lock Fast T or the mill-specified C-Lock Fast X that can effectively equal a Cat 6A cable type solution. On the optics side, here again you see an evolution away from discrete physical contact type solutions using either expanded beam or physical contacts to more array-based, denser solutions, even at the I/O panel and even between systems. And the other thing that begins to become apparent and useful in level 6 is the option, particularly when you're retrofitting a system and you have a unit that has electrical I/O inherently on the output panel, is to move the optoelectronic conversion into that level 6 interconnect. Make an active optical cable that's designed for the environment that you're trying to work in and do the conversion outside of the box. Oftentimes that can give you a fairly straightforward distance extension on an otherwise legacy application without redesigning the inside of the box. So if you just want to summarize some of the key points as you look at the trends in copper and fiber optic interconnects, copper's continuing to increase speed. I think several people have talked about that today. There's backplanes that support 25 gig and higher type solutions. The contact densities have increased 2 to 3 times in recent time. And there are higher speed copper I/O cabling solutions out there. But ultimately you run out of distance. For those of you that like to watch high definition football, if you know anything about uncompressed empty video, you know you can go 100 meters on a cable. So you put your HD camera in that end zone, you put your truck in that parking lot, and you can't get there from here. And once you open that option to use optics, what you'll find from that example and others is people take advantage of the bandwidth. And then all of a sudden, everything's on that fiber. Your Ethernet, your audio, your video, your data pipes all move to use the bandwidth of that otherwise available infrastructure. So the point there is that fiber can really help you as your data rates go up and your distances increase. That's pretty obvious. And as one guy told me once, fiber optics are glass, they break. It's really not true. When you look at the history and the pedigree of a lot of the optical solutions that are out there today, they've been time tested, they've been proven in military and other applications. And as you can see by some of the examples I've shown, they're keeping pace with the density of the optical traffic that you need to move the data that some of these solutions now require. So, real simple, quick example, if you're looking at a system, we try to take a look at it from a systemic perspective. What is the system problem you're trying to solve? So if you look at things like operating environment and you talk about harnessing, there was a really good example from the Radial folks of how you might look at handling an internal harnessing example. What about that cable on the outside? Is it going a few meters, or does it need to go across the muddy field and survive being run over by an Abrams tank? So what kind of connectors do you choose? What kind of cabling do you choose that can survive that type of an environment? How fast is the data you're moving and how far are you going is often an important question, but even inside the box, you may find that an optical ribbon or an optical flex circuit is the solution because of this compressed space that you have. But if you don't protect that properly, it may not survive the liquid cooling environment and the temperature swings involved, or the vibration-induced abrasion that'll happen over the use of the system in the field. So how do you protect the cables? How do you create those harness solutions to protect the fiber and take advantage of it without exposing its weaknesses? And then finally, you really need to understand what optical transceivers, what optical I/O you have at the end of those links. Are they parallel? Are they discrete? Are they pigtailed? Because all of those details affect how you choose the contacts that you might use, the types of interconnects you might use, where you might put connections or not, as the case might be. Things that can not only affect your link level performance, but also can become problems as you build systems. You need to think about what happens if I damage something as I'm putting a system together. What do I do about that? What do I risk in terms of the cost of transceivers versus cabling? Things like that all have to be considered based on the space and the available room that you have. And so one of the things that I've noticed that I run into a lot is it's really important to take a look at that optical link at the system level, because when you really look at how much optical link budget you often have, there's usually quite a bit there, and it's a lot better than it was 15, 20 years ago. And so I've seen many cases where you'll have component level devices like connectors get way overspecified. They'll ask for performance requirements that when you look at the system level link budget and what you're actually trying to accomplish, you've basically done nothing but add cost and an expense to a component. It doesn't need to be anywhere near that high performance, and the link will still survive in the environment, still operate just fine. So things to think about. And then the last thing I'm going to touch on before we wrap up and we can all start speed dating is you've heard me mention physical contact and expanded beam. And for those of you that don't know what that means, I just thought I'd take a minute and explain it. Physical contact is exactly that. When you have fiber optics, you bring them together under a controlled force, depending on the type of terminal you have. And why do you do that? You do that so that you get the insertion loss and the return loss performance that you need in your system to meet the specifications of that connection. Expanded beam is exactly what it says. You do not bring the contacts together. You put lensing elements between them, and you literally create a very small free space gap between the halves of the connectors. There's pros and cons with that. You saw an interesting example of doing free space optics in the free space transceiver that Radial talked on. That's another application for it. And because they're different physics, there are trade-offs. There are advantages and disadvantages. So for example, if you take a physical contact connector and made it out of the box, that's probably about the best you're going to get from a connector performance spec short of a splice until you made it 50 times in a dirty environment. Now, maybe not so much because you've damaged the end faces on the fibers. So when you look at the trade-offs here, you'll see things like where expanded beam may suffer an insertion loss, but then you go down and look at mating durability, the exposure to dust, and it has some definite advantages. So it depends on your system. Are you going to put the connection together and leave it? Or is it a field deployable section where you have to take this apart over and over and over again, and you really don't know who's going to be cleaning it, if at all? So with that, I will thank you for your attention, and I'll be happy to tackle any questions. Thanks.